This video is brief introduction of the Border Gateway Multicast Protocol, that is BGMP, a protocol for interdomain multicast routing. BGMP builds shared trees for active multicast groups and optionally allows receiver domains to build source-specific interdomain distribution branches where needed. BGMP natively supports source-specific multicast, that is SSM. To also support any source multicast, that is ASM, BGMP requires that each multicast group be associated with a single root. That is, in BGMP it is referred to as the root domain. It requires that different ranges of the multicast address space are associated with different domains. Each of these domains then becomes the root of the shared domain trees for all groups in its range. Multicast participants will generally receive better multicast service if the session initiator's address allocator selects addresses from its own domain's part of the space, thereby causing the root domain to be local to at least one of the session participants. It has been suggested that interdomain any source multicast is better supported with a rendezvous mechanism whereby members receive source data packets without any sort of global broadcast. PIM, SM and CBT use a shared group tree to which all members join and thereby hear from all sources. BGMP natively supports source-specific multicast, that is SSM. To also support any source multicast, that is ASM, BGMP builds shared trees for active multicast groups and allows domain to build source-specific interdomain distribution branches where needed. Building upon concepts from PIM, SM and CBT, BGMP requires that each global multicast group be associated with a single root. However, in BGMP, the root is an entire exchange or domain rather than a single router. For non-source specific groups, BGMP assumes that ranges of the multicast address space have been associated with selected domains. Each such domain then becomes the root of the shared domain trees for all groups in its range. An address allocator will generally achieve better distribution trees if it takes its multicast addresses from its own domain's part of the space, thereby causing the root domain to be local. BGMP uses TCP as its transport protocol. This eliminates the need to implement message fragmentation, retransmission, acknowledgement, and sequencing. BGMP uses TCP port 264 for establishing its connection. This port is distinct from BGPs port to provide protocol independence and to facilitate distinguishing between protocol packets. Two BGMP peers from a TCP connection between one another and exchange messages to open and confirm the connection parameters. They then send incremental, joint, or prune updates as group memberships change. BGMP does not require periodic refresh of individual entries. Keep alive messages are sent periodically to ensure the liveness of the connection. Notification messages are sent in response to errors or special conditions. If a connection encounters an error condition, a notification message is sent and the connection is closed if the error is a fatal error. Let us take a brief overview of protocol. BGMP maintains group prefix state in response to messages from BGMP peers and notifications from MIGP components. Group shared trees are rooted at the domain advertising the group prefix covering those groups. When a receiver joins a specific group address, the border router towards the root domain generates a group-specific join message, which is then forwarded border router by border router towards the root domain. BGMP join and prune messages are sent over TCP connections between BGMP peers, and BGMP protocol state is refreshed by keep alive messages periodically sent over TCP. BGMP routers build group-specific bidirectional forwarding state as they process the BGMP join messages. Bidirectional forwarding state means that packets received from any target are forwarded to all other targets in the target list without any RPF checks. No group-specific state or traffic exists in parts of the network where there are no members of that group. BGMP routers optionally build source-specific unidirectional forwarding state only where needed. To be compatible with source-specific trees, that is SPTs, used by some MIGPs, or to construct trees for source-specific groups. A domain that uses an SPT-based MIGP may need to inject multicast packets from external sources via different border routers, which thus acts as surrogates. Data packets are forwarded based on a combination of BGMP and MIGP rules. The router forwards to a set of targets according to a matching SG BGMP tree state entry if it exists. If not found, the router checks for a matching star G BGMP tree state entry. If neither is found, then the packet is sent natively to the next hop EGP peer for G according to the multicast RIB. If a matching entry was found, the packet is forwarded to all other targets in the target list. In this way, BGMP trees forward data in a bidirectional manner. If a target is an MIGP component, then forwarding is subject to the rules of that MIGP protocol. Now let us take a look on design rationale. Several other protocols or protocol proposals build shared trees within domains. The design choices made for BGMP result from our focus on interdomain multicast in particular. The design choices made by PIM-SM and CBT are better suited to the wide area intradomain case. There are three major differences between BGMP and other shared tree protocols. 1. Unidirectional versus bidirectional trees. Bidirectional trees, that is using bidirectional forwarding state as described before, which minimizes third-party dependence, which is essential in the interdomain context. Second, source-specific distribution trees or branches. In a departure from other shared tree protocols, source-specific BGMP state is built only where A. It is needed to pull the multicast traffic down to a BGMP router that has source-specific S and G state, and second, that router is not already on the shared tree, that is, has no star or G state, and third is that router does not want to receive packets via encapsulation from a router which is on the shared tree. BGMP provides source-specific branches because most MIGP protocols in use today build source-specific trees. BGMP's source-specific branches eliminate the unnecessary overhead of encapsulation for high data rate sources from the shared trees ingress router to the surrogate. Moreover, cases in which shared paths are significantly longer than SPT path will also benefit. However, except for source-specific group distribution trees, we do not build source-specific interdomain trees in general because 1. Interdomain connectivity is generally less rich than intradomain connectivity. So, shared distribution trees should have more acceptable path, length, and traffic concentration properties in the interdomain context than in the intradomain case. And second, by having the shared tree state always take precedence over source specific tree state, we avoid ambiguities that can otherwise arise. In summary, BGMP trees are, in a sense, a hybrid between PIM-SM and CBT trees. And third is method of choosing root of group shared tree. The choice of a group's shared tree root has implications for performance and policy. In the intradomain case, it is sometimes assumed that all potential shared tree roots within the domain are equally suited to be the root for a group that is initiated within that domain. In the interdomain case, there is far more opportunity for unacceptably poor locality and administrative control of groups shared tree root. Therefore, in the intradomain case, other protocols sometimes treat all candidate roots, that is RPs, cores, as equivalent and emphasize load sharing and stability to maximize performance. In the interdomain case, all roots are not equivalent, and we adopt an approach whereby a group's root domain is not random but is subject to administrative control. Protocol details. 1. Interaction with the EGP. The fundamental requirements imposed by BGMP are that 1. For a given source specific group and source, BGMP must be able to look up the next hop towards the source in the multicast RIB, and second, for a given non-source specific group, BGMP will map the group address to a nominal root address and must be able to look up the next hop towards that address in the multicast RIB. BGMP determines the nominal root address as if the multicast address is a unicast prefix based multicast address, then the nominal root address is embedded unicast prefix padded with a suffix of 0 bits to form a full address. Point second, multicast data packet processing. For BGMP rules to be applied, an incoming packet must first be accepted. 1. If the packet arrived on an interface owned by an MIGP, the MIGP component determines whether the packet should be accepted or dropped according to its rules. If the packet is accepted, the packet is forwarded or not forwarded out any other interfaces owned by the same component as specified by MIGP. Second, if the packet was received over a point-to-point interface owned by BGMP, the packet is accepted. And third is, if the packet arrived on a multi-access network interface owned by BGMP, the packet is accepted if it is receiving data on a source specific branch. If it is the designated forwarder for the longest matching route for S or for the longest matching route for the nominal route of G. If the packet is accepted, then the router checks the tree state table for a matching of S and G entry. If one is found but the packet was not received from the next hop target towards S or was not received from the next hop target towards G, then the packet is dropped and no further actions are taken. If no S and G entry was found, the router then checks for a matching star or G entry. If neither is found, then the packet is forwarded towards the next hop pair for the nominal route of G according to the multicast RIB. If a matching entry was found, the packet is forwarded to all other targets in the target list. Forwarding to a target which is an MIGP component means that the packet is forwarded out any interfaces owned by that component according to that component's multicast forwarding rules.